Humanity is about to take its greatest leap since the moon landing. We are standing at the edge of a new space age, one defined by missions that will completely redefine our future. These are not just journeys of exploration, they are quests that will answer the fundamental question of whether we are alone, unlock resources that could power our civilization for centuries, and establish our first permanent homes on other worlds. By the end of this, you will know the 25 missions that are set to change everything. We are hunting for life in hidden oceans and preparing to mine asteroids for unimaginable wealth. What do you believe is our ultimate destiny among the stars? Our journey begins with a world cloaked in ice, orbiting a distant giant. Europa, one of Jupiter's many moons, appears as a cracked and frozen marble, but beneath its serene surface lies one of the most promising environments for life beyond Earth we have ever discovered. The compelling evidence points to a global ocean, a vast body of salty water hidden beneath an icy shell miles thick. This is not a small sea. Scientists estimate this subsurface reservoir holds more than twice the liquid water of all the oceans on our own planet combined. It is a staggering thought, a hidden aquatic world waiting in the profound darkness of space. To investigate this potential oasis, NASA is building the Europa Clipper, a spacecraft of extraordinary sophistication. Its mission is not to land, but to perform dozens of close flybys, sweeping over the moon's surface to scrutinize it with a powerful suite of instruments. It will use ice-penetrating radar to peer beneath the crust, mapping the depth and structure of the ice and searching for pockets of water closer to the surface. Its spectrometers will analyze the composition of the surface, looking for organic compounds and salts that could have welled up from the ocean below. Every measurement is designed to answer one overarching question: is Europa habitable? Could its dark, deep ocean possess the chemical energy and the right conditions to support living organisms, even in microbial form? The Clipper is our best hope for finding biosignatures, the faint chemical traces that would signal we are not alone in the cosmos. The most direct path to discovering life, however, does not require drilling through the ice. Europa may be offering us a free sample. The Hubble Space Telescope and subsequent data have hinted at colossal plumes of water vapor erupting from fractures in the icy crust, spewing material from the hidden ocean hundreds of miles into space. The Europa Clipper is designed to fly directly through these suspected plumes. Its instruments will act like a chemical laboratory, analyzing the vapor and ice particles for complex organic molecules, salts, and even potential biosignatures. It is a cosmic fishing expedition where the spacecraft casts its net into these fleeting geysers, hoping to catch the chemical evidence of a living world. Yet, to truly confirm life, we may need to go to the source. The ultimate goal is a lander mission, a daunting technological challenge. This craft would have to touch down on the treacherous, cracked terrain and then find a way to reach the ocean, sealed away under a shell of ice that could be 10 to 15 miles thick. One concept involves a nuclear-powered cryobot, a probe that would literally melt its way down, inch by painstaking inch, over the course of many months. It would descend through a world of absolute darkness and crushing pressure, a journey to an alien abyss no human technology has ever attempted. What could possibly survive in such an extreme environment, cut off from sunlight and the surface? The best clues come from our own planet, from the deep sea vents on Earth's ocean floor. There, in total blackness, entire ecosystems thrive, powered not by photosynthesis but by chemosynthesis. Strange creatures like giant tube worms and blind shrimp draw energy from the toxic, mineral-rich fluids spewing from the Earth's crust. If life exists on Europa, it may be clustered around similar hydrothermal vents on the ocean floor, feeding on chemical energy. Finding such organisms would revolutionize our understanding of biology, proving that life is not a fragile anomaly but a persistent, powerful force that can flourish in the most unexpected places in the cosmos. While Europa offers the tantalizing possibility of life hidden away in the dark, our own moon presents a more immediate and audacious challenge. We are going back, but not for a fleeting footprint. This time, the goal is to build a home. NASA Artemis program is the monumental architecture behind this permanent return to the lunar surface. It begins with the most powerful rocket ever built, the Space Launch System, a colossal vehicle designed to propel humanity beyond Earth's orbit once more. Its companion is the Orion spacecraft, a state-of-the-art capsule that will carry astronauts on their journey, providing a safe habitat for the multi-week voyage to the moon and back. But the true departure from the Apollo era is the Gateway. Imagine a small space station, a bustling outpost in orbit around the moon, serving as a staging point, a science laboratory, and a temporary home for crews. This gateway is the crucial hub, the port from which landers will descend to the surface and where long-term lunar operations will be coordinated. The destination itself marks a historic shift. Artemis aims to land the first woman and the next man not on the familiar, sun-baked equatorial plains, but at the lunar South Pole. This region is a land of extremes, with crater rims in perpetual sunlight and deep, frigid basins shrouded in permanent shadow. It is within these dark, cold traps that scientists believe vast reserves of water ice are locked away, preserved for billions of years. This water is the key to everything. It is not just for drinking. It can be split into hydrogen and oxygen, the very components of breathable air and powerful rocket fuel. Finding and utilizing this resource would transform the moon from a destination into a gas station, a vital waypoint for humanity's deeper journeys into the solar system. This lunar gateway is far more than a simple way station. Think of it as a command center and a proving ground, the first permanent human outpost in deep space. From its orbit around the moon, it will coordinate the complex ballet of lunar landings, serving as a communications relay that ensures astronauts on the far side of the moon are never out of touch with Earth. But its true purpose extends far beyond our celestial neighbor. The gateway will be a laboratory where we learn to live and work in the deep space environment, testing new technologies and studying the long-term effects of radiation and microgravity on the human body. These are the critical lessons we must master before we can even contemplate the much longer, more dangerous journey to Mars. The entire architecture of Artemis, from the gateway to the base camp at the South Pole, is designed around a single, transformative principle: sustainability. The era of planting a flag and leaving is over. We are now entering the age of in situ resource utilization, a complex term for a beautifully simple idea: living off the land. Instead of hauling every drop of water and every breath of air from Earth at astronomical cost, we will learn to extract what we need from the moon itself. Those shadowed craters at the South Pole are not just scientific curiosities. They are our future gas stations and grocery stores. Robotic rovers will be the first prospectors, venturing into the eternal darkness to drill for and analyze the water ice. Once confirmed, the real work begins. Massive, automated processing plants could one day harvest this ice, melting it for pure water, and using solar or nuclear power to split it into its core elements, hydrogen and oxygen. Oxygen for astronauts to breathe, and hydrogen and oxygen combine to create rocket propellant. This changes the entire economic equation of space exploration. A lunar outpost that can refuel spacecraft transforms the moon into the most valuable port in the solar system, a springboard from which missions to Mars and the asteroids become infinitely more feasible and affordable. The dream is no longer just to visit another world, but to truly make it our own. But our search for life extends far beyond our solar system, into the depths of the galaxy. Orbiting 1,000,000 miles from Earth, the James Webb Space Telescope is our most powerful window into this cosmic ocean. This observatory is not merely a telescope, it is a time machine. By gathering the faint infrared light that has traveled across the universe for billions of years, it allows us to witness the birth of the very first stars and galaxies, seeing them as they were when the cosmos was in its infancy. This deep cosmic stare is possible because Webb sees the universe in infrared light, a form of invisible heat radiation. This is the key to its power. Cosmic dust, which obscures the view of optical telescopes, is virtually transparent to Webb's infrared eyes. It can peer through these vast clouds to watch stars being born in stellar nurseries and see the structures of ancient galaxies with a clarity we have never before achieved. Yet one of its most revolutionary roles is much closer to home in a sense. It is analyzing the atmospheres of worlds orbiting other stars. When an exoplanet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Webb's exquisite instruments can dissect that light, spreading it out into a spectrum, a chemical barcode that reveals the gases present. It searches for the subtle fingerprints of molecules like water vapor, carbon dioxide, methane, and even oxygen. On Earth, these gases, especially when found together, can be powerful biosignatures, indirect evidence of biological processes. The telescope is not looking for little green men, but for the chemical whispers of a living world. Finding a distant planet with an atmosphere rich in oxygen and methane would be a discovery of profound magnitude, a strong hint that we are not the only life in this vast and silent universe. The true magic of this cosmic detective work lies in a technique called transit spectroscopy. When a distant world passes in front of its star from our point of view, a tiny, almost imperceptible fraction of the star's light does not simply vanish. It filters through the planet's thin, gassy envelope, its atmosphere. During this brief celestial alignment, molecules in that alien air absorb specific colors of the starlight. The James Webb Space Telescope is exquisitely tuned to catch this faint, filtered light. It breaks the light down into a spectrum, a brilliant rainbow of information where missing lines and bands act as a unique chemical barcode. Each dip in the light tells a story, revealing the presence of water vapor, the signature of carbon dioxide, or even the tantalizing hint of methane. Finding these gases in the right combination around a rocky planet could be our first real clue, the first whisper of a biosphere at work. One of the most promising places to hunt for these whispers is a system known as TRAPPIST-1. This is not a single star system like our own, but a much cooler, smaller red dwarf orbited by a family of 7 rocky worlds. 3 of these planets orbit within the star's habitable zone, that theoretical band where temperatures might be just right for liquid water to exist on their surfaces. 7 Earth-sized targets around a single star. It is a veritable treasure trove for astronomers. Webb has already begun a deep, systematic study of each of these worlds, measuring their atmospheres one by one. The question is profound. Are any of them wrapped in an atmosphere that could support life as we know it? A detection of oxygen and methane together would send shockwaves through the scientific community, as these gases typically cancel each other out unless they are constantly replenished, potentially by living organisms. This is not about finding cities or signals, but about reading the very air of another world and discovering it is being breathed. Reading the air of distant worlds is a profound step, but to truly know a planet, we must hold a piece of it in our hands. This is the ultimate goal of one of the most ambitious robotic endeavors ever conceived, the Mars Sample Return Campaign. This is not a single mission, but a carefully choreographed interplanetary ballet involving multiple spacecraft from NASA and the European Space Agency, all working in perfect harmony to achieve one objective: to bring the first pristine pieces of Mars back to Earth. The first act of this epic is already underway, playing out on the rusty surface of the Jezero crater. The Perseverance rover is our robotic field geologist, tirelessly traversing an ancient river delta, a location scientists believe is one of the most likely places to have once supported microbial life. Its core task is to seek out rocks and soil that hold the greatest scientific promise. using a sophisticated drill on its robotic arm. Perseverance is not just studying these samples in place, it is carefully sealing them inside ultra-clean titanium tubes, creating a library of Martian history. It then deposits these precious tubes at a designated cache site on the surface, a celestial time capsule waiting for a future courier. That courier is the next critical piece of the puzzle, the sample retrieval lander. This massive lander, a future mission, will make the daring journey to Mars, touching down with pinpoint precision near the cache site. It will carry two remarkable pieces of technology. The first is a fetch rover provided by the European Space Agency, which will scurry out, locate the scattered sample tubes and gather them up. The second, and perhaps the most audacious component, is the Mars Ascent Vehicle. This will be the first rocket ever launched from the surface of another planet. Once the samples are safely loaded into a special container at the top of this small rocket, the Mars Ascent Vehicle will ignite its engines and scream through the thin Martian atmosphere, carrying its priceless cargo into orbit. But the journey is only half over. Waiting in that orbital parking lot will be the Earth Return Orbiter, another ESA contribution. This spacecraft must perform a delicate, autonomous rendezvous, capturing the basketball-sized container as it floats in the void of space. Once secured, the orbiter will seal the container within a robust biocontainment system, ensuring that no Martian material ever contaminates Earth's biosphere during the long cruise home. The final act is a fiery re-entry over a military testing range in Utah, where the sample return capsule will parachute to the ground, finally delivering its otherworldly treasure to a waiting team of scientists. The analysis that will follow inside maximum security laboratories is beyond anything we can do with rovers. We will be able to slice the rocks thinner than paper, peer at them with microscopes 1,000,000 times more powerful than those on Mars, and search for the subtlest chemical and physical traces of ancient life. This is not just about bringing back rocks, it is about bringing back answers to questions that have haunted humanity for centuries. Did life ever take root on another world in our solar system? The evidence may be sealed inside those tubes, a secret waiting to be unlocked right here on Earth. The secrets locked within those Martian tubes will not give up their answers easily. Unlocking them requires the full might of Earth's scientific arsenal, capabilities that simply cannot be packed into a rover, no matter how advanced. Back in our most sophisticated laboratories, scientists will subject these samples to a level of scrutiny that is almost unimaginable. They will slice the rocks into sections thinner than a human hair, revealing their microscopic structures under electron microscopes. They will vaporize tiny fragments to analyze their exact chemical and mineral composition with mass spectrometers, instruments so sensitive they can detect parts per billion. This is the kind of precision needed to find the faintest traces of organic molecules, the building blocks of life, or even to identify microscopic fossilized structures, the ghostly imprints of ancient Martian microbes. The ultimate dream, however remote, would be to find something more, evidence of extant life, organisms that might still be clinging to existence in sheltered subsurface niches, their biomarkers preserved within the samples. To handle such a monumental discovery and to ensure absolute safety, an unprecedented level of planetary protection is already being implemented. The samples will be treated as potentially hazardous until proven otherwise, a necessary precaution to prevent any possible contamination of Earth's biosphere. A state-of-the-art receiving facility is being designed, a maximum security laboratory unlike any other. The Martian material will be contained within multiple layers of sealed enclosures, manipulated by scientists using robotic arms through glove ports, similar to how dangerous pathogens are handled. This is not about fear, but about responsibility, preserving the pristine nature of the samples for study while safeguarding our own world. The entire endeavor hinges on a single, profound possibility. This mission could provide the first definitive evidence that life is not a unique phenomenon of Earth. A positive result would mean that life arose not once, but twice independently within our own solar system. If it happened here and it happened next door on Mars, then the universe must be teeming with life. The answer to one of humanity's oldest questions may be landing in the Utah desert, sealed inside a canister. Yet the search for life demands we explore environments far stranger than the cold deserts of Mars. Far out in the solar system, orbiting the ringed giant Saturn, lies a world that is at once eerily familiar and utterly alien: Titan. This is not a barren rock. Titan is a world shrouded in a thick, hazy orange atmosphere, a place with its own active weather cycle. It has rivers carving through landscapes, great lakes pooling in basins, and clouds that release a steady drizzle of rain. But this is where the familiarity ends. On Titan, the temperature is so brutally cold, hundreds of degrees below zero, that water is frozen solid, as hard as granite. The liquid that flows here is not water, but methane and ethane, hydrocarbons that exist as gases on Earth but form vast, frigid seas on this distant moon. This is a world with chemistry completely different from our own, a frozen time capsule that might hold clues to how life began. To navigate this bizarre and complex environment, NASA is building a machine unlike any that has ever flown on another world. The mission is called Dragonfly, and it is a revolutionary nuclear-powered rotorcraft, essentially a large, sophisticated drone. Titan's thick atmosphere and low gravity make it an ideal place for flight, a stark contrast to the thin air of Mars. Dragonfly will not merely land in one spot. It will use its set of rotors to lift off, fly for miles, and land in a new location of scientific interest, turning an entire region of Titan into its laboratory. Its primary mission is to investigate the moon's complex probiotic chemistry. The surface of Titan is covered in organic compounds, the carbon-rich building blocks necessary for life as we know it. Scientists believe Titan's environment, with its hydrocarbon lakes and water ice crust, may mirror the conditions of a primordial Earth frozen in time. Dragonfly will land in an area of vast sand dunes made of organic grains, near an impact crater where scientists believe liquid water once mixed with the surface organics. It will use a sophisticated suite of instruments to taste the surface, drilling for samples and analyzing them for the types of complex molecules that could have eventually led to life. This is not a direct search for living organisms, but a journey to the very cradle of chemistry, to understand the steps that can lead from simple ingredients to the spark of biology. What will this drone discover as it hops across an alien landscape under the dim orange glow of a distant sun? It may just find that the recipe for life is more universal and more robust than we ever dared to dream. Dragonfly's mission is to trace the chemical pathways that could lead from simple molecules to the spark of life itself. The key to this quest lies in the bizarre, carbon-rich sludge that coats Titan's surface, a substance scientists call tholins. These are not simple compounds, but complex organic polymers that form when sunlight breaks apart methane and nitrogen in the moon's upper atmosphere. The resulting particles drift down, blanketing the landscape in a thick, orange haze and settling into dunes that stretch for miles. This ongoing chemical rain makes Titan a massive, natural laboratory for probiotic chemistry, a frozen experiment showing us the steps that might have occurred on Earth billions of years ago before biology ever began. Titan presents a radical alternative to our water-based story of life. On our world, water is the essential solvent, the liquid medium in which the molecules of life dance and combine. But on Titan, water is rock, and the liquid roles are played by methane and ethane. This forces us to ask a fundamental question: how far can the dance of chemistry progress in a world without liquid water? Dragonfly is designed to answer that. It will land in the Shangri-La Dune Fields, a region rich in these complex organic sands, and then fly to the Selk impact crater, a location where a past impact likely melted the water ice crust, creating a temporary pool of liquid water. This is the perfect place to investigate. The drone will use a drill to collect samples of both the dry organic dunes and the material from the crater floor where water and organics once mixed. Its onboard mass spectrometer will then act as a molecular taste test, identifying the specific compounds present and determining their complexity. Is it just a tarry sludge of simple chains, or are there more advanced structures, the precursors to amino acids and the nucleobases that form our genetic code? By studying these two different environments, Dragonfly will show us how far chemical evolution can go in a cold hydrocarbon soup, and whether a brief encounter with liquid water can kickstart the process even further. The implications are staggering. If we find that Titan's chemistry has naturally produced the advanced building blocks of life, it would mean the recipe for life is not a fragile one-planet wonder. It could be a common, almost inevitable process written into the fundamental laws of chemistry across the cosmos. While Dragonfly traces the chemistry of a single world, our next mission will capture the grand motion of the entire cosmos. The Vera C. Rubin Observatory represents a fundamental shift in how we observe the universe, moving from taking snapshots to recording a continuous, decade-long movie of the sky. Perched on a mountaintop in Chile, its primary instrument is not just a telescope but a revolutionary machine, the largest digital camera ever built for astronomy. This camera boasts a staggering 3.2 gigapixels, a resolution so immense that it would take over 1,500 high-definition television screens to display just one of its full images. Every few nights, this incredible eye will complete a fresh scan of the entire visible sky, a task that would take other telescopes years to accomplish. This relentless, all-seeing survey is officially known as the Legacy Survey of Space and Time, a name that perfectly captures its epic ambition. Over 10 years, it will not simply look at the sky, it will watch it night after night, compiling a cosmic motion picture of unprecedented scale and detail. The result will be a catalogue of over 20 billion galaxies and a similar number of stars, mapping the structure of our universe with a clarity we have never before possessed. But this mission is about more than just creating a static map. By comparing each night's images to the last, the survey will detect anything that moves, blinks, or changes. It will flag millions of transient events, from asteroids zipping through our own solar system to distant supernova exploding in far-off galaxies. It will track the subtle, rhythmic flickering of stars, revealing the presence of orbiting planets. It will even chart the slow, gravitational dance of stars within galaxies, providing crucial new data on the invisible pull of dark matter. This is a mission designed to find what we are not looking for, to uncover the mysteries we have not even thought to question yet. What hidden patterns and cosmic rhythms will reveal themselves when we finally have the patience to watch the entire sky for an entire decade? The true power of the Vera C. Rubin Observatory lies in its ability to see the invisible. Its grand survey is designed to tackle the two greatest mysteries in modern cosmology: dark matter and dark energy. These two invisible components are thought to make up 95% of the universe, yet we know almost nothing about them. The observatory will investigate dark matter not by seeing it directly, but by witnessing its profound gravitational influence on the light from distant galaxies. This effect is called weak gravitational lensing. Imagine space-time as a vast, flexible sheet. A massive object like a cluster of dark matter creates a dimple in this sheet. When light from a galaxy billions of light years away travels toward us, its path bends as it passes near this invisible dimple, subtly distorting the galaxy's image. By meticulously measuring the tiny, twisted shapes of millions upon millions of galaxies, the Rubin Observatory will effectively trace out the hidden scaffolding of dark matter that spans the cosmos. It will create the most detailed map ever made of this unseen cosmic architecture, revealing how this mysterious matter is woven through the universe. At the same time, the survey will take aim at an even more puzzling force, dark energy. This is the name given to whatever is causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate. The observatory will measure this acceleration with breathtaking precision by cataloging a specific type of stellar explosion, a supernova known as a standard candle. By tracking the brightness and distance of thousands of these supernovae across cosmic time, scientists can chart how the expansion rate has changed over billions of years. This data could finally tell us whether dark energy is a constant force or something that varies, potentially rewriting our most fundamental laws of physics. But while its gaze is fixed on these cosmic horizons, the observatory will also perform a vital task much closer to home. Its rapid, repeated scans of the sky make it the most powerful asteroid hunting machine ever built. It is expected to increase the catalog of known objects in our solar system by a factor of 10, spotting millions of new asteroids and comets. This comprehensive inventory is our first and best line of defense, identifying any potentially hazardous objects on a collision course with Earth decades or even centuries in advance. It may even catch another fleeting visitor from interstellar space like Oumuamua, helping us understand how common such travelers are. From the invisible threads of dark matter binding the galaxies to the rocks tumbling through our own celestial backyard, this single observatory will give us our first complete picture of the dynamic universe we call home. While the Vera C. Rubin Observatory charts the cosmos from Earth, another revolutionary eye is being prepared to launch into the void. The Nancy Grace Roman Space Telescope, named for NASA's first chief astronomer, is not just another telescope. It is a machine built to answer two of the most profound questions in science. What is the universe made of, and how many other worlds are out there? Designed as a wide-field cousin to the Hubble and Webb telescopes, Roman possesses a unique superpower, a panoramic view of the cosmos. Its primary camera has a field of view 100 times larger than Hubble's infrared instrument. This means that while Hubble is like looking at the sky through a soda straw, seeing incredible detail in a tiny patch, Roman is like throwing open a giant picture window, capturing vast cosmic landscapes in a single, sweeping glance. This incredible breadth allows it to perform wide-area surveys hundreds of times faster than Hubble could ever manage. Where Hubble might spend weeks piecing together a mosaic of a single galaxy cluster, Roman will capture the same richness of detail across thousands of clusters in the same amount of time. It is an observatory built for speed and scale, designed to conduct a census of the universe itself. Its mission is twofold: to unravel the mystery of dark energy and to find thousands of new worlds beyond our solar system. To understand dark energy, the force accelerating the expansion of the universe, Roman will employ its wide gaze to map the three-dimensional distribution of matter with exquisite precision. It will use a technique called gravitational lensing, watching how the light from billions of galaxies is subtly warped by the invisible dark matter that surrounds them. By tracking how this cosmic web has evolved over billions of years, the telescope can measure the precise push and pull of dark energy throughout cosmic history, potentially revealing its true nature. At the same time, Roman will embark on the largest planetary search in history. It will use a method called microlensing, which relies on a beautiful cosmic coincidence. When a star in our galaxy passes precisely in front of a more distant star, the foreground star's gravity acts as a lens, magnifying the background star's light for a few weeks or months. If the foreground star has a planet orbiting it, that planet will create its own, smaller spike in brightness. This technique is exceptionally sensitive, allowing Roman to find planets that are incredibly far away, even free-floating worlds untethered to any star, drifting alone in the interstellar dark. The telescope is expected to discover thousands of these distant worlds, building a statistical understanding of planetary systems across the galaxy. Are solar systems like ours the rule or the rare exception? The Nancy Grace Roman Space Telescope will give us the numbers, painting a true portrait of our galactic neighborhood and perhaps revealing just how crowded the cosmos really is. This microlensing technique is a form of celestial sleight of hand, a fleeting alignment that reveals what is normally hidden. It works because gravity, according to Einstein's theory, warps the very fabric of space and time. A massive object, like a star, acts like a lens in this warped space. When this foreground star drifts into perfect alignment with a much more distant background star, as seen from our vantage point, something extraordinary happens. The foreground star's gravity bends and focuses the light from the background star, causing it to temporarily brighten. From Earth, we see the distant star flare up for a period of weeks or months before fading back to its normal state. This event is a cosmic mirage, a gravitational magnifying glass. Now, imagine that the foreground star has a planet orbiting it. As that planet moves around its star, it can also pass in front of the distant star's light path. The planet's own gravity creates a secondary, much smaller and sharper spike in brightness superimposed on the main event. That tiny, telltale blip is the signature of a new world. This method is uniquely powerful because it does not rely on the planet blocking its star's light or causing a stellar wobble. It relies solely on gravity, which means it can find planets that are incredibly far from their host stars in orbits that would take centuries to complete. It can even detect planets floating entirely alone in the dark, worlds that were flung from their birth systems and now wander the galaxy as permanent nomads. Roman survey will catch thousands of these brief, bright alignments, and in doing so, it will unveil a hidden population of planets we have never been able to see before. The galaxy may be filled with these rogue worlds, outnumbering stars by a staggering margin. What does it mean for a planet to exist in the absolute cold and dark of interstellar space, with no sun to warm it? Could some of these drifting worlds, insulated by thick ice shells or internal heat, harbor deep, hidden oceans where life clings to existence around geothermal vents? The Roman telescope will not see these surfaces, but it will tell us how common such orphans are, forcing us to expand our very definition of a habitable world. While Roman peers into the galactic dark, another mission is turning its gaze inward toward a world that serves as a stark warning. Venus is Earth's twisted sister, a planet of terrifying extremes. Its surface is hot enough to melt lead, crushed under an atmosphere 90 times thicker than our own, and shrouded in clouds of sulfuric acid. Yet there is compelling evidence that this hellscape was not always so hostile. Billions of years ago, Venus may have been a temperate world, complete with shallow oceans and a climate that could have been conducive to the emergence of life. The Da Vinci I+ mission, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a daring quest to uncover what went so catastrophically wrong. This is not just a mission to another planet, it is a detective story, an investigation into a planetary crime scene, seeking to understand the processes that can turn a potential paradise into a furnace. The spacecraft itself is a two-part system consisting of a main orbiter and a robust spherical descent probe. The orbiter will circle Venus, using its cameras to map the surface in unprecedented detail, focusing on unique geological features called tesserae, which may be ancient continents, the last remaining evidence of a lost, more Earth-like world. But the heart of the mission and its most dramatic moment is the descent of that probe. It will be released into the upper atmosphere, a one-way journey into the abyss. As it falls for roughly 1 hour through the thick, poisonous clouds, it will be the first spacecraft to directly sample Venus's atmosphere since the 1980s, and it will do so with technology that is orders of magnitude more advanced. The descent sphere is a fortified laboratory designed to survive the corrosive clouds and immense pressures. Its suite of instruments will act like a vacuum cleaner, constantly sniffing the air as it plunges downward. It will measure the precise concentrations of noble gases like krypton and xenon. These inert gases are the ultimate tracers as they do not react with other elements. Their ratios act as a permanent record, telling scientists whether Venus started with the same primordial ingredients as Earth, or if it formed under different, drier conditions. The probe will also hunt for specific isotopes of lighter elements like hydrogen. The ratio of different types of hydrogen atoms can reveal the planet's history with water. A specific signature would be the smoking gun, definitive proof that Venus once possessed vast quantities of water that later boiled away into space. This is the central mystery. How did a world that might have been lush with water become a bone-dry inferno? The leading theory is a runaway greenhouse effect, a cautionary tale for our own planet. On Earth, carbon dioxide in the atmosphere traps just enough heat to keep us warm. On Venus, something triggered a feedback loop. Perhaps its closer proximity to the Sun caused its early oceans to evaporate. Water vapor is a potent greenhouse gas trapping more heat, which evaporated more water until the entire planet was caught in a thermal trap. The carbonates that would normally lock away carbon dioxide in rocks, as they do on Earth, were baked out of the surface, releasing all of the planet's carbon back into the atmosphere, creating the crushing, heat-trapping blanket we see today. Da Vinci Plus will test this hypothesis by analyzing the chemistry of the atmosphere layer by layer, searching for the chemical ghosts of that lost ocean. As the probe nears the surface, its hardened camera will snap the first ever high-resolution pictures of the tesserae landscape during descent, giving us a ground-level view of what may be the oldest terrain on the planet. This mission will tell us more than just the history of Venus. It will tell us about the fragility of habitable worlds and the fine line between a temperate Earth and a scorching wasteland. The descent probe's final moments will be its most revealing. As it plummets through the thick, yellow haze, its hardened camera will be fixed on a target of profound geological importance, a vast, fractured highland region known as a tessera. These are not simple mountains, but complex, ridged landscapes that look like cracked, ancient puzzle pieces shoved together. On Earth, such complex, interlocking formations are the hallmark of plate tectonics, the slow, grinding dance of continental plates that recycles carbon, regulates climate, and ultimately helps maintain a planet's long-term habitability. The camera's last images, snapped just before the probe is crushed by the immense surface pressure, will provide our first ever close-up view of this terrain. Scientists will scrutinize every ridge and valley, searching for the telltale signs of compression and extension, the geological fingerprints of tectonic forces. If the tesserae show clear evidence of having been pushed together and pulled apart over vast stretches of time, it would be a monumental discovery. It would mean that Venus, our hellish neighbor, was once a dynamic world with a moving, shifting crust, a planet that may have actively managed its climate and interior heat much like Earth does. This single finding would transform Venus from a static cautionary tale into a world with a complex and active geological history, a place that could have potentially maintained stable conditions for life over billions of years before its climate spiraled out of control. The data from Da Vinci Plus will help answer one of planetary science's biggest questions. Is plate tectonics a rare geological fluke, or is it a common, even necessary, process for creating and sustaining a habitable world around a star? The answer lies locked in the cracked highlands of a lost world. Venus holds a stark warning about planetary fragility, but our next journey seeks out worlds where oceans still flow, hidden beneath frozen shells. The European Space Agency is preparing to dispatch the Jupiter Icy Moons Explorer, a mission known by its fitting acronym, JUICE. This ambitious spacecraft is setting its sights on the king of planets, Jupiter, but its true targets are the monarch's mysterious, ice-clad satellites. JUICE will conduct a grand tour of 3 extraordinary moons, Ganymede, Callisto, and Europa, each believed to harbor vast subsurface oceans. Its mission is to characterize these hidden aquatic worlds, probing their depths to determine if they could be habitable environments. The spacecraft is a flying fortress of scientific instruments, equipped with powerful radar to sound the icy crusts, magnetometers to sense the conductive saltwater layers beneath, and cameras to map the complex, fractured surfaces in stunning detail. But its most historic maneuver will come at the journey's end. After a series of intricate flybys, JUICE will do what no spacecraft has ever done before. It will brake, fire its engines, and slip into orbit around Ganymede, the largest moon in the entire solar system, a world even bigger than the planet Mercury. Orbiting Ganymede will be like having a front-row seat to an alien ocean world. The spacecraft will study its unique, intrinsic magnetic field, the only moon known to possess one, which creates a miniature magnetosphere within the vast, dominating field of Jupiter. This protective bubble likely plays a crucial role in shielding the moon's surface and potentially its subsurface ocean from the intense radiation that bathes the Jovian system. By mapping Ganymede's ice shell and probing its hidden ocean, JUICE will help us understand how such a large, complex world can maintain liquid water so far from the Sun. What does it mean for a moon to be so active and dynamic, a place with its own magnetic shield and a deep, dark sea? This mission will transform Ganymede from a distant point of light into a fully realized world, and in doing so, it may reveal that the most promising habitats for life are not planets at all, but the many ocean moons orbiting the gas giants of our solar system. This magnetic personality makes Ganymede utterly unique. While other moons are passive rocks or ice balls, Ganymede generates its own magnetic field from deep within, a churning dynamo of molten iron in its core. This creates a miniature force field, a tiny magnetic bubble around the moon. But Ganymede lies inside the most violent neighborhood in the solar system, the colossal magnetosphere of Jupiter. This creates an incredible celestial tug-of-war, where Ganymede's small field is constantly buffeted and reshaped by the king of planets. The JUICE spacecraft will fly directly into this interaction zone, using its sensitive magnetometers to map the invisible lines of force as they tangle and reconnect. These magnetic dances are not just an abstract spectacle, they have profound consequences for the moon's habitability. When Ganymede's field connects with Jupiter's, it can funnel intense radiation and charged particles down onto the moon's surface, bombarding the ice. But in other regions, its field might actually create a safe haven, a protected zone where the ice is shielded. Understanding this complex relationship is key to knowing what lies beneath. That is because JUICE will use the magnetic field as a tool to probe the ocean itself. Salt water is an excellent conductor of electricity. As Ganymede's internal ocean sloshes deep below the ice, it will create subtle, secondary ripples in the moon's magnetic field. By measuring these tiny fluctuations with exquisite precision, JUICE can effectively map the ocean's depth, its salinity, and even its currents without ever drilling through the ice. We will learn if this hidden sea is a stagnant, frozen layer, or a dynamic global ocean like our own, with movement that could transport nutrients and energy essential for life. Ganymede is not a simple ball of ice. It is a complex, layered world, a planetary onion with a metallic core, a rocky mantle, and a vast shell of water and ice. JUICE's detailed study of its gravity and shape will reveal how these layers are structured. Was its rock and ice fully mixed in the beginning, or did it form in a more orderly way, with heavy materials like iron and rock sinking to the center and lighter water rising to the top? This process, called differentiation, is what created the Earth's metal core and rocky crust, and it is considered a fundamental step for creating a geologically active world. Finding that Ganymede underwent this same process would elevate it from a mere moon to a planetary embryo, a world that started down the same path as Earth but was frozen in time. Could such a world support life? It possesses the three key ingredients: liquid water, a source of energy from its heated interior and tidal squeezing by Jupiter, and a rich chemistry of organic compounds likely embedded in its ice. Ganymede may represent an entirely new class of habitable world, one where life thrives not on a sunlit surface, but in a dark, deep abyss, cradled by the gravitational pull of a giant. Deep in the asteroid belt between Mars and Jupiter spins a world unlike any other. This is the asteroid 16 Psyche, a 200-kilometer-wide object that shines with a strange metallic glint. While most asteroids are rocky or icy leftovers from the solar system's formation, Psyche appears to be something far more extraordinary. Scientists believe it is the exposed, metallic heart of a doomed protoplanet, a world that was almost fully formed in the solar system's violent infancy. Billions of years ago, this nascent planet likely suffered catastrophic collisions, its outer layers of rock violently blasted away, leaving behind only its dense metallic core to drift through the ages. This is not just another space rock, it is a time capsule, a pristine relic from an era of planetary birth and destruction. We have never seen anything like it up close. The cores of rocky planets, including Earth, are hidden away beneath thousands of miles of rock and mantle, utterly inaccessible. They hold the secrets to our planet's magnetic field, its internal heat, and its very structure. Psyche offers us the one and only chance to look upon a planetary core directly. To seize this opportunity, NASA has built a mission bearing the asteroid's name. The Psyche spacecraft is a robotic explorer equipped with a suite of instruments designed to investigate this metallic world. It carries a multispectral imager to map the surface in incredible detail, spectrometers to determine the exact composition of the metal, and a magnetometer to search for any remnant of an ancient magnetic field. The journey itself is a marvel of engineering, utilizing highly efficient solar electric propulsion. This system uses electricity from the spacecraft's vast solar arrays to accelerate ions of xenon gas, creating a gentle but continuous thrust that will push the craft across millions of miles of space. It is a slow and steady race to a world of iron and nickel. What will we find when we arrive? If Psyche is indeed a naked core, its surface should be a bizarre landscape of metal canyons, solidified metal lava flows, and colossal cliffs forged in the ancient collisions that shaped it. The mission's magnetometer will listen for the ghost of a magnetic field, a faint echo from when the core was still molten and churning. Finding such evidence would be like discovering the fossilized heartbeat of a planet that never was. This journey is not about mining or resources, it is pure planetary archaeology. By studying Psyche, we are reading the very first chapter of our own world story, a chapter written in iron that has been lost to time on Earth. It answers a fundamental question about how planets are built from the inside out. Peering into Psyche is like opening a time capsule from the solar system's violent birth. We have never directly observed a planetary core before. Our own Earth's molten heart is locked away beneath thousands of miles of impenetrable rock. This mission offers our one and only chance to see one firsthand, a glimpse into the hidden engine room of a world. By carefully mapping Psyche's metallic terrain and analyzing its composition, scientists can test our fundamental theories of how rocky planets are built. We believe that in their infancy, all terrestrial worlds were molten balls, heated by the energy of countless collisions and radioactive elements. In this molten state, gravity caused the heaviest materials, primarily iron and nickel, to sink inward, forming a dense core, while lighter silicates rose to the surface, creating a crust. This process, called differentiation, is the defining event that creates a layered planet like Earth, Mercury, Venus, or Mars. But how exactly does this happen? Is it a single, rapid event or a slow, complex separation? Is the core a pure sphere of iron-nickel alloy, or is it mixed with lighter elements like sulfur or silicon that change its properties? The answers are literally written in the metal of Psyche's surface. The spacecraft's instruments will act as forensic tools reading this metallic text. Its spectrometers will determine the exact blend of elements, revealing the core's recipe. High-resolution images will show us the topography, the canyons and cliffs shaped by eons of cooling and contraction, and perhaps even the scars from the colossal impact that stripped this protoplanet bare. One of the most critical investigations will be for a magnetic field. A magnetic field is generated by a churning, liquid metal core, a dynamo effect that acts as a planet's protective shield. Earth's strong magnetic field deflects harmful solar radiation, making surface life possible. Did Psyche's core once churn and generate its own field? The spacecraft's magnetometer will search for any faint, fossilized magnetism locked within the ancient metal, a ghostly remnant of a dynamo that died billions of years ago. Finding it would be profound, confirming that this exposed core was once a dynamic, molten engine. This single mission will transform our understanding of planetary formation, moving from theoretical models to direct observation. It reveals the foundational processes that built our own world and shaped its capacity for life. What other secrets are waiting, frozen in that lonely sphere of metal, drifting between the orbits of Mars and Jupiter? The hunt for water on the Moon now moves from orbit to the ground with a robotic prospector designed to touch the ice itself. NASA Viper rover, the Volatiles Investigating Polar Exploration rover, is a mobile robot destined for the most extreme environment on the Moon, the permanently shadowed craters of the South Pole. Its mission is not merely to confirm that water ice exists, but to become the first ever resource mapper for another world, creating a detailed blueprint of where the water is, how much there is, and how it is mixed with the lunar soil. This is a critical step, turning scientific speculation into a practical plan for survival. The rover is a solar-powered machine, but it is engineered to navigate an area of eternal twilight. It will venture into the profound cold of these shadowed regions, its batteries charged by the sun on nearby illuminated ridges before it drives back into the darkness to conduct its work. Viper carries a sophisticated suite of instruments, but its most important tool is a 1-meter drill capable of pulling up samples from beneath the surface. These samples will be analyzed by onboard spectrometers, which can detect the unique chemical signature of water molecules and other volatile compounds. The rover will do this repeatedly across different types of terrain, from cold traps to slightly warmer areas, building a 3-dimensional understanding of this frozen reservoir. This data is the key to our future. Knowing exactly where to find high concentrations of water ice will determine where we build our first permanent lunar bases. This water is the cornerstone of a self-sustaining presence, providing not just life support for astronauts, but the literal fuel for deeper exploration. The ice can be processed into liquid water, breathable oxygen, and most importantly, hydrogen and oxygen for rocket propellant. The Moon could become the first interplanetary gas station, and Viper is the surveyor plotting the very first pump. What it finds will dictate the roadmap for everything that follows, transforming a distant dream of a lunar colony into an achievable logistical reality. This transforms the Moon from a destination into a cornerstone of our spacefaring future. The discovery of water ice is not just a scientific triumph, it is the spark for an economic revolution. The sheer cost of escaping Earth's gravity is the single greatest barrier to deep space exploration. Launching a single kilogram of material into orbit requires a staggering amount of fuel, and every drop of water, every tank of air, every liter of rocket propellant needed for a journey to Mars must be hauled up from our planet at an astronomical price. But what if we could stop carrying all that weight? This is the promise of a lunar gas station. Water, that simple molecule, is the key. Through a well-established process called electrolysis, solar or nuclear power can be used to split water into its 2 elemental components, hydrogen and oxygen. These are the very same propellants that power the main engines of countless rockets. a lunar outpost that can mine ice and manufacture fuel, breaks the logistical chain that has always tied us to Earth. Suddenly, a spacecraft bound for Mars does not need to be fully fueled for its entire journey at launch. It can be launched with just enough propellant to reach the Moon, refill its tanks at a lunar depot, and then embark on its interplanetary voyage with a full load. This slashes the initial launch mass from Earth by more than half, making missions profoundly cheaper and more frequent. This is the birth of a cislunar economy, a bustling sphere of commercial activity between Earth and the Moon. Private companies could launch satellites from the Moon's low gravity far more efficiently. Tugboats fueled by lunar propellant could repair and reposition satellites in Earth orbit. The water itself becomes a commodity, sustaining not just astronauts but entire industrial operations. The Moon becomes a port, a warehouse, and a factory, all rolled into one. This is no longer just exploration. It is the opening of the first off-world frontier, fundamentally rewriting the economics of our future in space. But the most ambitious journey of all aims not for a planet or a moon, but for another star. The Breakthrough Starshot Initiative is a vision so bold it seems plucked from science fiction, yet it is backed by serious science and significant funding. Its goal is to launch a fleet of miniature probes, each no larger than a postage stamp and weighing barely a gram, toward our nearest stellar neighbor, the Alpha Centauri system. These tiny star chips will be the smallest and fastest spacecraft ever built, equipped with microscopic cameras, sensors, and communication systems. Their propulsion would not come from bulky rockets, but from an immense array of powerful lasers based right here on Earth. This ground-based light beamer would focus a concentrated beam of light onto the ultra-thin, reflective sails attached to each star chip. The constant pressure from this laser pulse would push the tiny craft, accelerating them to a previously unimaginable velocity, up to 20% of the speed of light. At that staggering pace, a journey that would take a conventional spacecraft tens of thousands of years would be slashed to a mere 20 years of travel time. Imagine these tiny light sails, smaller than your hand, surfing a beam of light across the cosmic ocean, carrying the eyes of humanity to another sun. The challenges are monumental, from building a laser array the size of a city to protecting the fragile chips from interstellar dust during their high-speed dash. Yet if it succeeds, within our lifetimes we could receive the first close-up images of an alien planet orbiting another star, a blurry picture that would forever change our place in the universe. These tiny star chips face engineering hurdles of almost unimaginable scale. The first is their sail, the very fabric that must catch a beam of light. It cannot be a simple sheet of cloth. It must be a marvel of nanotechnology, a light sail only a few hundred atoms thick. This membrane must be perfectly reflective, incredibly strong, and weigh almost nothing. Even a single grain of interstellar dust colliding at 20% the speed of light would be like a nuclear explosion for such a delicate object. The sails might need to be able to detect and avoid these microscopic hazards autonomously, or be designed in a way that allows them to survive countless tiny punctures without losing their shape or function. The propulsion system back on Earth is no less daunting. To push these gram-weight probes to such incredible velocities requires a laser array of staggering power, a coordinated network of beams combining into a single gigawatt-class push. This is not a single laser pointer, but an infrastructure project, a phalanx of emitters spanning potentially kilometers. They must all fire in perfect unison, focusing their energy onto a sail the size of a picnic table that is already thousands of miles away and receding faster than a bullet. The precision required is like using a spotlight in New York to consistently illuminate a moving coin in London, while that coin is accelerating toward the horizon. And then there is the star chip itself, the entire spacecraft. It must carry a power source, a camera, a processor, and a communication laser, all miniaturized onto a single silicon wafer smaller than a postage stamp. Its camera lens would be smaller than a pinhead, its transmitter weaker than a smartphone's. After its 20-year journey, this tiny probe must then turn itself toward Earth and successfully beam its precious data across the 4.37 light-years of empty space, a signal so faint it will be all but lost in the background noise of the cosmos. This mission represents a total reinvention of space travel, a shift from the thunderous fire of chemical rockets to the silent, graceful push of light. It trades immense mass for immense speed, brute force for exquisite precision. The challenges are profound, but the reward is a new chapter in our story, one where the stars are no longer destinations for our distant descendants, but places we can reach within a single human lifetime. From the hidden oceans of Europa to the ancient metal heart of Psyche, these missions weave a single, breathtaking narrative. We are no longer content to simply look up at the stars. We are reaching out to touch them, to taste their alien waters, and to walk upon their soil. We are hunting for the faintest whispers of life in the atmospheres of distant worlds and preparing to build our first permanent homes on the moon. We are planning to bring back pieces of Mars and to send our smallest creations to another sun. This is not a scattered collection of projects, it is a coordinated surge, a species-wide awakening to its own potential. Each mission, in its own way, is a critical piece of a much larger puzzle, the puzzle of our future. Together, they mark a profound historical pivot, the moment we stop being fleeting visitors in the cosmos and begin the long, arduous, and glorious work of becoming a multi-planetary civilization. The future you have seen in science fiction is not a distant fantasy. It is a blueprint, and its foundations are being laid right now in clean rooms and laboratories around the world. The greatest adventures in human history are unfolding before our eyes, so watch these missions closely, share in their discoveries, and let your own curiosity be ignited. For the next chapter of our story is not being written by fate, but by the determined hands and brilliant minds of